And since this is AIRC sponsor update, it's somewhat redundant to acknowledge, but I'd like to go ahead and acknowledge it. So thank you very much. And this particular presentation today, first introduce this, and next we talk about the digitization video and the summary of deliverable and future opportunities. So approximate time frame of our project on right hand side. Objective, as we start working on additive manufacturing, I'm not necessarily going to any details, but as you know that CNC machining, but CNC machining removes material versus additive manufacturing added material. So you have this sort of huge deal with the data. Digital engineering is a kind of important because additive manufacturing allows you to have your own printer. So being able to have a good data, most updated data at your print shop becomes important. So talk about digital engineering, the framework. So that's effectively what it is. Right-hand side, we have a organization, sort of a nice figure, simplified figure, but all the levels make decisions. Smallest, the lowest level, we make very more like a acquisition type of decision, but all level needs to provide certain feedback. And at the end of the day, we can make a good decision. So this tool that we developed allows us to have this combined effort from all levels, then we can make a good. And we have the use cases we took. So some definitely different type situation where we have aircraft fleet maintenance. We have one type of use case we did. Use case we did. And based on use case, we understand what factors needed for decision making. And so we try to come up with so deliverable this particular project, we have an element of a three different use cases and do analysis, data analysis, then do the software too. So that's something almost repeating the same process that as described previously, but that's what we did. And strategy. You see the right-hand side, you have this system engineering is a iterative process. That's something you learn first when you're in university. And so starting with a thread at the top, you come up with needs. Particular loop, you have a design here. So from top to bottom, you're going to from needs requirement to this. Everything looks good. We can start dealing with manufacturing, how we can make this manufacturing. Then obviously that's where the additive manufacturing is. If this is a life cycle type situation, we have to think about what happened at the end of your product life. So how we can support after the production become obsolete. Then this obviously going back to the needs. So the second half goes from bottom to top. So it's top down, bottom up approach as some of the people. So this circular approach, but also at the same time, you're doing the top down, and bottom up. And as you start dealing with digitization, in fact, that's a quite large situation. You cannot And data can be technical data or non-technical data. So we selected technical data. And within technical data, we have technical product. White one, data to technical product, all the way to the product design. And this within product design, we have this, we sort of try to digitize our effort and try to understand. So if you think about the other way, if you start going non-technical data and what to do, logistics, how to deal with the work in progress, and what do you want to keep the most updated date. So when you say production ended, the most updated sounds kind of strange because so production ended, the design is the end, but that's not the case, because many times when the production ended, people start still using those equipment. And once you're in the field and something breaks, you have to use AM to use those printed AM part as a part of your service. So those things becomes important. But in our project, we did not address this end of life type situation. Anyway, so when we did it, part producibility as well as repeatability. So, and then reproducibility. If those data is compatible, of course, you can make entire thing as one loop, and you can do some type of a scenario and set input, then you can scenario. So you can do some kind of parametric study. Obviously, we haven't gotten that part yet, but that's something is possible. But at the first very step, you have to understand each step and find out what is their input and their output at each process. So that's always saying in this part. And start what we can use. So this use case, we use the satellite data and satellite design and manufacturing of this part. So first, satellite part, we picked the satellite part, basically. And it has to be manufacturable as well. Then try to understand the objectives and the requirement based on your mission, basic mission thread, basically, what the requirement is for your satellite case. Then try to construct what's on the utility function. Making tool, and we call this decision engine that allows us to help us to do making some decisions. Setup. We have certain structure that we have to know. So you cannot adjust everything, but again, you have to pick certain fields. So this bus platform is the one that our focus was, and it has structure frame, proportion, etc., thermal system. So certain things we have to understand those. So we pick this left-hand side. This is bracket for additive manufactured bracket for this gimbal assembly. That's a part. We pick this left-hand side. This is an existing additive manufacturing application for the satellite. And first thing is, you have to go the requirement. So we did the SysML. You try to understand what is required using this diagram. And many times when you make a screenshot from, for instance, Cameo, it's very too small to show. So prepare the next slide. So this shows a little bit better view. So we have a basically structure requirement of this gimbal. So performance means, so what type of size we're looking for. If this part is way too big, you cannot print. It has to be within a footprint of your 3D printer to be able to do additive manufacturing. For the material, what density you're looking for, if it's too dense, not too dense. Mechanical properties of the material that needs to meet, then what temperature, and Young's modulus are another mechanical properties, but then what temperature we need. But our structural requirement is for this part. And you have to define this separately in the requirement table that I will explain next. So first, our performance. So this is before you selecting material. So you have mission thread, and we have to understand what type of mechanical properties or thermal property you need for that particular mission. So those are ones that's first selected. So we can have minimum, maximum. So some are quite large range, and some simply specify the minimum requirement, etc. How much cost we have. This is per 1,000 for this 12 million. So each one $12,000 per part, basically, if you average this. If this is an automotive parts, it's way too expensive per parts. It's all entire vehicle might do some pick and some specify the production time. Next, what happens is when we pick material, it needs to be used with certain additive manufacturing machines. So you have a combination of material and machine. Then if you select, for instance, stainless steel, aluminum, you can make same part, but selection of material, it limits certain printing machines. So there's a machine material sort of a combination. Manufacturing forged material. So we can compare 3 additive manufacturing versus 1 traditional manufacturing, so we can see the difference among them. And so if you, for instance, if you take additive manufacturing titanium of this size, density, and mechanical properties, and ductility, etc., etc. So without going too much detail, just allows us to see what type of material, machine, and then you have some restriction in the mechanical. My cost $500,000 or even $0.1 million. It's not that super expensive, but once you start trying to do this, you cannot disregard in addition to the initial purchase of your part. Then those are time just to make 1,000 part, how long it takes. Just put some numbers here based on some literature review, but we have to also specify this for your decision engine. And so summary of this particular, in our case, we picked some bracket assembly. Then based on the mission we have, we found the requirements. And based on this we created some input information for the decision engine. Then we made one. I want to point out that to create this type of requirement, that took a long time. For instance, this used 23 reference materials, etc. So at the end of the day, we'll talk about the future action later, but somehow we need to wait. We need to find a way to minimize make it. I want to do some demo of a software decision engine. And so one more time, how this some sort of a data in JSON format, and place this as a feedback input for your decision engine level, whether he or she wants to be risk seeking or risk averse. So some people like to, for instance, this attribute versus utility. You think about this being, say, for instance, money you want to spend in horizontal end of day, your utility. So some people want to spend a lot of money to have a very large results. Those are risk-seeking behavior versus people don't want to spend a lot of money. So those are the risk averse, and people who don't belong to neither of those are just risk neutral. Those are straight lines showing up. So this we hard coded this type of a behavior. Actually, we took everything as a risk neutral straight line, but additive manufacturing material machine model. And going to a little bit of detail of this software. So gives information for decision engine, and decision engine has basically a logic inside, multiple if statement, if this happens, parts inside. Then at the end of the day, we come up with a ranking of alternatives. So try to make our decision making easy for the users. This is demo starting from next part. Click this. So you can start immediately seeing results. And this one, you see the left-hand side, you have alternatives. If you pick one of those, each large number, time is very important. Okay, you went really fast. So I'm going to say, if I can go back a little bit. And here, for instance, you can time and cost. If time is very important, you can put the weight very important for you. You put the cost very, very high number, but the time is less. So that totally depends on the application. For instance, if you're dealing with as well as space applications, your cost may, okay, so you have to reduce cost, but not as much as, for instance, time. Or some case you want to really save money, but time is not important. So that's something you can choose at this point. You pick, and your expected the utility side change. So you expect utility means, this is a ranking. So higher this bar is, more like you. It shows you have cost and time, those two change. So right now we have this cost is more important for time. That's what we're saying. Time. If you have this alternative number one, which is effectively this first, this cubed, this particular set of additive manufacturing makes sense the most. Then if very important, then you can choose alternative number 4, which is this binder jet, the red one showing. So this allows combination of machine material makes the most sense. That's effectively what it is. And from this point, summary of our deliverable is, first we came up with a framework for the digital engineering. Try to come up with a requirement, then utility function and range for each attributes, basically. That's what we did. And talk about the future opportunities. So what we came up with this part, decision engine task 4. So this is what we came up with. Right now, it sits right now, but as we said, you can make some improvement. So opportunity number 1 is model-based system engineering. I want to feed the material directly from MBSE. Number 2 is this red one, blue one says AWB2 or Analytic Workbench 2, something the Purdue team came up with under Dr. De Laurentiis. And if we can use our decision engine as an input for this one of the tool called RPO or Robust Portfolio Optimization, which is part of AWB. So that's opportunity number 2. Opportunity number 3 is we can connect our tool with a there's no way you can do this. But if you're connected to the material database, you can definitely do sensitivity study even before part being built. So it's kind of doing a fine. We can derive our we can derive our design using generative design tool. So changing certain parameter in the CAD drives everything change. So that's why we can even put the IP database as part of our system, and we can do sensitivity analysis. So conclusion, basically, that's what it is. We came up with a good tool, and we want to continue our research, but depends on listening to my presentation.
Thank you, Waterloo. Any questions from the room here? I have one question.
What they're doing. So any type of proprietary information that you can obtain from database mechanical properties or some materials that you didn't know existed or something like that, then you can use this as part of parametric study. So you might be considering magnesium works better, lighter material, lighter or something like that, and you can end up choosing. So having IP database connected to the decision engine definitely is a positive for your design, sort of like a brainstorm.
So another quick question: is it possible to, through the system models, integrate multiple parts together, like two materials that can't touch?
Yes. So biomaterial can be very, very difficult part because between the interface. So if we are to do this system engineering, we have to also have some type of a material compatibility type study. Temperature, it might not work well. So restrictions up to a certain temperature, this works, but from a certain temperature beyond, it doesn't work. And part of this as part of a logic.
Potentially capture those design rules.
We have not yet captured yet, but it is possible. Yes, it's actually called metal cladding. Cladding is a word you use just to describe two materials joined together, and you can actually. Yeah. Thank you.
Okay. Other questions? Thank you, Waterloo.
Thank you. Appreciate it. Thank you.
That ends this session. I think it's lunchtime.